We will continue with our 12th lecture, and in this lecture I am going to introduce the notion of stability for the first time. So we can talk about the stability of control systems from both open loop and closed loop perspective. But as far as I am concerned, once we explain the notion of stability, whether it's open loop or closed loop stability, the ideas are pretty much the same, except there will be a difference in the transfer function that you're looking at. So basically what I'll try and do in this lecture is explain to you when a system is stable, and we'll draw upon what we have learned in terms of analysis of transfer functions using partial fraction expansion, and you will see the power of that idea when we try to understand stability. So any system now which in time domain I said would be ordinary differential equations, modeled as ordinary differential equations, and once we do the Laplace transforms, these equations get converted into what we call as transfer functions. And if we talk about stability of a system, we talk about the stability properties of the ordinary differential equations that are used to model the system, and consequently we talk about the stability of g of s, which is the transfer function model. So we will just talk about stability of transfer functions, and you will notice that once we understand the stability of transfer functions, then basically we do not really have to worry about stability of what Laplace variable we are interested in. So what I mean by this is, if I explain to you what the stability of this g of s is, how do you understand the stability of g of s, then if you define stability as output stability, that is, would my output be stable, and we will have to explain what stable means, then basically what you are looking for is the stability of y of s, which is not any different from g of s. It is just that y of s is g of s times u of s that we have seen before, and I could call this as some g y of s, right. So whatever ideas work here will also work here. So what we want to know is, in general, how do you understand stability for transfer functions. So what I am going to do is I am going to explain stability in a intuitive fashion. However, it does not mean that we are going to do any hand waving. All the results are exact, and there is nothing that we leave out, but because of the way in which we have shown how to expand these transfer functions in terms of partial fractions, it makes it very easy for us to define what stability means. So let us start. If we talk about the stability of the transfer function g of s, we are going to say this g of s is stable if the corresponding g of t, which you will get from inverse Laplace, which is a time domain function, is bounded for all time. So what do we mean by bounded? So if I have, let us say, simple layman understanding of this is, if I have t, if I have g of t and I plot this, it should not go like this and go to infinity, right. So I should be able to say g of t will be between certain values, okay. So that is the idea of g of t being bounded. So as t tends to infinity, g of t cannot tend to infinity, it has to be bounded between certain bounds. So how do we conceptually think about stability of g of s? While this definition of stability, very simple English language definition of stability, is very understandable, and we are just saying this does not go to infinity, right. However, how do I understand this mathematically is an important question that we should address. So remember that when we want to get g of s, we write this g of s some numerator by denominator, and then g of t is Laplace inverse of this numerator by denominator, and we have spent enough time in trying to explain to you that this numerator by denominator I can expand it in terms of partial fractions. The only type of terms that I get in the partial fraction are e power pt. So this type of term I will get if the root p is repeated only once, that is, it is a distinct root. Or I will also get this term if p is, let us say, repeated twice, the first term will look like this, but the second term will look like this, right, t e power pt. So remember we had this rule where if a root is repeated ki times, I will have ki terms, and the last term of that sequence will be s minus p to the power ki, and if I do the inverse Laplace of that, then I will get time to the power ki minus 1 e power pit and so on. So if you look at this, the type of terms that you are going to get when I do this expansion right here, the time terms are going to be e power pt, t e power pt, t squared e power pt, t cube e power pt and so on. Of course, around these terms there are going to be some constant, but those are constant numbers, so they are not going to be really influencing whether g of t is going to be bounded or unbounded. So, basically in general you can think of this as having c1 e power pt, c2 t e power pt kind of terms, right, c3 t squared e power pt and so on. Now, we can look at each of these terms individually and then look at these terms and ask the question, when would these terms go to infinity? Time tends to infinity. So, let us take a generic term which is t power r e power pt, and let us also assume in general the root can be complex. We will write the expansion here and then really talk about each one of these things carefully, and we can talk about what happens if the root is real, what happens if there is this pole is distinct and so on by looking at this generic term. So, as I said before, the expansion of gt or the time function of gt is going to have several terms which are of the form t power r e pt. R is 0 means you will get e power pt, r is 1 you will get t e power pt, r is 2 t squared e power pt and so on. So, you are not going to get any term outside of this form, right, because remember we are doing this for ns over ds. If your transfer function is not of the form ns over ds, where ns and ds are polynomials, where the order of ds is greater than the order of ns, then you have to think about other things. But as far as we are concerned till now, and I have shown you that most of the transfer function models still now that we are interested in are always having this form. That basically means that the sum of these terms can only have functional forms like this. So, let us take a generic functional form like this and then ask the question, as t tends to infinity, what will happen to this term? Now, if every one of these terms as t tends to infinity does not go unbounded, then we are in a good shape, right. But if there is some reason why, if as t tends to infinity, if some of these terms become unbounded, then we say the system is not stable. So, let us expand this. Now, let us say t power r e power a plus I b t. Now, if this particular pole is distinct, okay, and also real, then that basically means that since it is distinct I will never have the t term, because if it is distinct I will have only 1 by s minus p, which will be e power pt. So, r equal to 1 for this root. Now, if we also assume that it is real, then this term will simply boil down to e power a t. So, this is for poles that are real and distinct. So, poles that are real and distinct will only be able to generate terms like this. Okay. So, that is an important thing to remember. The notion of distinct is it is not repeated. So, it can have only one term which is 1 by s minus p. So, that will just be e power pt. So, r is 1, and here since it is real I am setting b equals 0. So, if your pole is distinct and real, then we can ask the question, this is one term in the sum and what will happen to this term e power a t. Okay. Now, if a is greater than 0, then this will become unbounded as t tends to infinity, right. So, if it is e power 2 t or e power 0.5 t and so on, so this will go to infinity. However, if a is less than 0, then this e power a t term is going to 0 as t tends to infinity. So, as long as the real part is less than 0, so we will come to the equal to line later. So, right now let us just talk about less or greater. Equal to, if you look at this, if you put a equal to 0, this will be 1. So, it is not unbounded, it is a bounded number, but for now we will focus on just the greater than 0 and less than 0. So, if I plot these roots in a complex plane, because the solution can be complex also. So, the real part will be here, the complex part I b will be here. So, what this says is if the root is real and if you want that term not to go to infinity, then basically it has to be on this side of this line, and I am drawing this line because we have assumed it is real. So, this I b does not come into picture. So, for a root that is real and distinct, if a is less than 0, that term will never blow up to infinity. Okay. So, that is something that you should keep in mind. Now, we are going to do this step by step and then we will write the final result, which is in this form. Now, if the root is real, but it is not distinct, let us say for example, it is repeated twice, okay, then the two terms I am going to get is I am going to get s minus p plus 1 by s minus p whole squared, because it is repeated twice I will get s minus p and s minus p squared, and we already have said many times this will give me a term e power t and this will give me a term e power t, and if p is real then it will become e power a t and t e power a t. So, these are two terms in the g t expansion that you will get. We have already discussed this term. As long as a is in the less than 0 or to this side of this line, then we know that this term will tend to 0 as t tends to infinity. Mathematically, it can also be shown that if you have a term like t e power a t, if a is less than 0, this t e power a t will also tend to 0 as t tends to infinity. This can be mathematically shown. Not only this, you can also show t squared e power a t will tend to 0 as t tends to infinity if a is less than 0, and so on. So, as long as you have a finite power of t and write t to the power e power a t, and if a is less than 0, then all of those terms will go to 0. So, what this basically means is essentially that it does not matter how many times the real root repeats, as long as the real part or the real root is less than 0, the terms that come out of these roots can never make GT go to infinity. So, these will still make GT stable. So, that is a key idea that you have to remember. So, let me repeat. So, if a root is real, it does not matter whether it is distinct or repeated many times, as long as a is less than 0, then you will have stability. As t tends to infinity, all of the terms that come out of these expansions will all go to 0. Now, let us take the case where I have a complex root, it is distinct. Okay. So, if I have a complex root that is distinct, that means I am saying I have a plus ib as one root. But remember, if a plus ib is one root, then a minus ib also has to be another root, a complex conjugate. So, whatever analysis I show for a plus ib will also work for a minus ib. So, let us take this t r e power a plus ib times t, because now the pole is imaginary. Now, if you take this t power r, let us say this pole is repeated r times, and now we can do this analysis without talking about distinct and non-distinct and so on, you will see why quickly. Then I have t power r e power a plus ib t, which I can expand as t power r e power a t e power ib t, and you know e power I theta is cos theta plus I sin theta. So, e power I b t can be expanded as cos b t plus I sin b t. Now, if you look at this term that has come out of an imaginary or a complex root which is repeated, if it is not repeated r will be 1, but we can address the whole case together, because we have already talked about repeated roots when we talked about real roots. Now, so there will be terms like this, right, and what we are doing is we are going term by term, right, and then seeing whether any of these terms can actually go to infinity. So, we are looking at it carefully in terms of term by term, and when I look at this, then I say okay, let us look at this as t tends to infinity. So, though the argument inside cos goes to infinity, cos itself is a bounded function. So, this cannot go unbounded. Similarly, while the argument here can keep going to infinity, sin itself is a bounded function. So, this cannot be unbounded. So, this whole thing can never be unbounded. It can be oscillatory, which is what we will see later, but it cannot be unbounded. So, really whatever be the b, it does not matter. So, what it says is irrespective of the b, right, whether b is positive, negative, does not matter, and whether t tends to infinity does not matter, because these two terms are going to be bounded. The stability of g of t depends only on this, and this is like the real root case that we have already talked about. As long as a is negative, this term can never be bounded. So, this term will go to 0 as t tends to infinity. So, because of this, irrespective of b being positive or negative, any time you have a negative, you will get the system to be stable. So, as long as all your roots are here, okay, which is all a is negative and irrespective of the value of b. So, b can be positive, negative, does not matter. So, this whole side is what is called left half plane, LHP. So, this is a thing that people use in control. So, as long as all your roots are in the LHP, so it does not matter whether it is here, here, here and so on, because for all of this, if you pull this down, the real part is always negative. So, as long as the real part is negative, those terms cannot create any problems. So, g of t will be stable. However, if even one root of g of s is in the right half plane, it does not matter where it is, it is here, here, it does not matter. Even if one root is on the right half plane, the system will become stable, because I might have n roots, n minus 1 of these could be on this side, only one root is on this side. However, when I expand this g of s, I will have a term for each of these n minus 1 and I will have one term for this, all of which are sum. So, n minus 1 terms will go to 0, but the nth term, because this a becomes positive, will necessarily go to infinity as t tends to infinity. So, that is what this thing says here. All the roots with negative real parts in the left half plane in a complex plot makes system stable, that is, if you have all your roots only in left half plane, it makes it stable. However, even if you have one root in the right half plane, then it makes the system unstable. So, this is a result that you might have seen before. This is the logic behind this result, and notice how I do not have to do anything more. This is a very general result, right, because I am assuming my function is of the form ns over ds. I have done partial fractions, there is no error in the partial fraction, there is no approximation in the partial fraction. So, if these are true, then it has to be necessarily true. So, this is the main result of stability. So, if I have a transfer function g of s, which can be written as a numerator transfer function by denominator transfer function, if I find the roots of the denominator transfer function and if I find all the roots of this denominator transfer function are in the left half plane, which basically means the real part of that root is strictly negative, then I call the system stable. Now, as I said before, you can also talk about stability of y of s. Now, when you talk about stability of y of s, we have two terms here. So, initially we only talked about stability of g of s, right. Now, I have y of s, which is g of s times I of s. So, while we can talk about stability of g of s, it is not necessary that y of s stability depends only on g of s, right, because y of s stability will also depend on I of s. Okay. So, to understand this, for example, if I write y of s as some numerator by denominator and I of s also as some numerator by denominator. Now, if you think of this itself as a whole y of s transfer function, as long as there are no cancellations in terms of roots between n1s and d2s or n2s and d1s, if there are no pole 0 cancellations as they call it, for this transfer function, the roots of this transfer function will be a collection of roots of d1s and d2s. Okay. So, just for the sake of illustration, let us say d1 has 2 roots p1 p2, d2 has 1 root p3, and as long as there is no cancellation, if I write this y of s as some n of s by d of s, clearly the d of s polynomial will have all the roots p1, p2, p3. So, when you expand this in partial fraction, you are going to get something like c1 by s minus p1. I am assuming each of these are distinct roots, c2 by s minus p2 plus c3 by s minus p3. And when you do the Laplace inversion of this, you are going to get c1 e power p1t plus c2 e power p2t plus c3 e power p3t, right. So, what you need to understand is every root of the denominator polynomial in g of s will introduce one term, and if it is repeated, it will introduce as many terms as the repeat, and every root in the I of s transfer function denominator also will introduce a term. So, if you want y of s to be stable, basically we are looking at this whole sum of terms to be stable. That means I of s also has to be stable. Okay. So, when we come to y of s, we use this notion of bounded input, bounded output stability. So, what we are saying is if ut is bounded, when is yt bounded, right. So, given that ut is bounded, when is yt bounded. So, can I say for every bounded input yt will be bounded. Now, in the last slide we saw for g of t to be bounded, we said g of s should have all the poles in the left half plane. Similarly, for u of t to be bounded, u of s should have all the poles in its left half plane. So, if the poles of I of s or u of s is in the left half plane, then we call that as bounded ut or it. Now, I am using this term I of s here because this y need not be written in terms of just u of s, that is an open loop transfer function. Later we will see that y of s can be written in terms of some transfer function times a disturbance transfer function, or some transfer function times a set point transfer function, and so on. So, I have generalized that and then I am calling it as I of s. So, as long as this input I of s has all the poles in left half plane, then we will have a bounded input. So, when we have such a bounded input, then the output will also be bounded if all the poles of g of s are in the left half plane. So, that is an important idea, right. So, a Beebo stability would mean that my poles in the g of s should be in the left half plane, assuming that I have bounded input. That is the reason why I call it bounded input, bounded output stability. So, notice how when we talk about the stability of g of t itself, which where we talk about the stability of g of s, correspondingly the stability of y of s just becomes the stability of g of s if I of s is bounded, right. So, if I of s is bounded, we are only worried about g of s, right. Now, the reason why I left that line in the middle, which I did not talk about, we will come to later. So, I will introduce an interesting idea of how we think about that imaginary line and what happens if g of s has pole on the imaginary line. That is a very interesting idea and we will get back to this and understand that well as we go along. But just remember that the Beebo stability really depends on g of s if u of s is bounded, and we call u of s bounded when we have this the poles of u of s or I of s in the left half plane. Again, you could also ask the question, what happens if one of the poles of I of s is on the imaginary axis? That could still be a bounded input function. I have left that now because I am going to come back to that. It introduces some interesting ideas and we will see that presently. So, let us take a quick look at how some of these come together. So, when we look at the behavior of let us say y of s, then in typical terms you could have let us say a system which responds, which is stable with no oscillations. It could be unstable with no oscillations, it could be stable with oscillations, it could be unstable with oscillations, and so on. So, these are possibilities when we talk about stability in oscillations. And then if you want to understand from a transfer function viewpoint, how does all of this come about? It is a simple idea here. So, if you have let us say a transfer function where the poles are strictly in the left half plane, and let us take the case where the poles are on the real axis in the left half plane, then you know whenever I have poles like this, the kind of terms I will get will be just e power p1 t, and since this pole is on the real line, I am going to get something like e power at where a is negative. So, I cannot get any oscillations if the poles are strictly on the real line on the left half plane. However, if I have poles like this, right, then what I am going to get is I am going to get terms of the form a plus ib times t. This is going to be e power at cos bt plus I sin bt. Now, as t tends to infinity, because I am showing these poles on the left half plane, a is negative. So, this is going to go to 0, but it will take a while before it goes to 0. However, in the meanwhile, because of the cos and sin terms, I will have oscillations. So, I will have oscillations which are damped, which means that I start like this and then the oscillation will keep decreasing till it goes 0. So, that is why I get damped oscillations. These oscillations come from this term, and the damping out or dying out comes from the e power at term if a is negative. Now, if I have poles roots of g of s only on the imaginary axis, then I could have A is 0. So, I will have just e power I b t, which will give me cos b t plus I sin b t. Now, if you notice that this is oscillating, because it is directly on the imaginary axis, there is no e power a t term to either let it die or let it increase. So, basically this will be sustained oscillations whenever you have poles on the imaginary line. And now the extensions are quite simple. If you have a pole on the real line on the right half plane, this will be unstable because I will have e power a t term where a is positive. So, as t tends to infinity, it will go to infinity, and if I have on the right half plane I have imaginary part to the pole root also, then I will get e power again a t cos b t plus I sin b t. So, these terms will introduce oscillation, this will keep increasing. So, you will have oscillations which keep growing and then becoming unstable. So, these kinds of plots which you have seen before, you can quite easily understand when you think about this simply in terms of partial fractions, right. You do not need any other mathematical machinery other than this partial fraction idea, because all you are looking for is terms of the form t power r e p t, that is it, right. And this here I explained without repeats and so on. So, the same idea is valid if you have roots that repeat. For example, if I had one imaginary root that repeats twice, then I will have terms such as this, and I will have another extra term t e power a t cos b t plus I sin b t for the repeat. Now, notice that this oscillations will still be there here, and this term we said will die down to 0 if a is negative. So, the same idea works. So, you will have oscillations which get damped as t tends to infinity, this term will go to 0 and this oscillation will get damped out. So, look how beautifully we can understand all the behavior with just partial fractions, and you do not have to understand anything other than the fact that every term in this expansion is of the form t power r e p t. So, there is a particular input function that is of importance in control systems. This is called frequency response analysis of the system. We will come back to this in more detail later. So, typically if you have a physical process, what you could do is you could give a sine input to the process and then see how the output looks. So, remember the tank example that we keep talking about, there is an outlet, there is an inlet. Now, if you keep increasing and decreasing the inlet and see what happens to the outlet, you expect it to increase and decrease. Now, understanding how the output behaves for a signal like this is what is called as frequency response analysis, and we call this a frequency response analysis because the input is let us say a sine wave, then this W represents the frequency with which we are oscillating this input. So, we want to see how this frequency oscillation changes the output. So, the way we usually do, let us illustrate this for a very simple first order example. Let us say I have a process which is first order, then the corresponding transfer function is k over tau s plus 1. And remember, I said the way you do it is you do the Laplace transform of the input to the Laplace domain, and you will see from your table quite easily this is a I w s squared plus w squared. Y of s is simply a product of this and this. So, I will have tau s plus 1 a I w by s squared plus w squared. Now, if you were to do the partial fraction expansion method, here are details, I would let you work this out, but if you finally simplify all of this, you will get y of t in a time form like this. I encourage you to really work this out for yourself, and we will also give you a homework assignment on this so that you really practice this and understand this, because this is very important from a control viewpoint where we talk about frequency response analysis. So, notice that for an input, so now I translate this to here. So, for an input a I sin omega t, I am going to get an output a naught sin omega t plus phi. Okay. Now, the interesting thing to notice is what this says is if your process is linear, if you perturb the process at some frequency omega or w, the output will also be perturbed at the same frequency omega or w. However, the input amplitude will get modified to an output amplitude a naught, and there will be something called a phase lag or lead that is introduced here from the sine. Okay. So, if I have something like this as the input, sustained sine. So, the output could be lagged, but at the same frequency as the input. So, that is what this says. Now, in this case you will notice, we can generalize this later, in this case you will notice that you can compute this A naught if you do all of this computation here as aik divided by root of 1 plus tau squared omega squared. So, this will come out of this computation, and there is a significance to this, and this phi will come out as tan inverse minus t omega. So, now if you notice this expression, right. So, I can take this A naught by ai to the other side, I have k divided by root of 1 plus tau squared w squared. Now, if you notice this, this is what I am going to call as a gain ratio. Why do we call it as a gain ratio? Because I sent in an amplitude of ai, but the output amplitude is a naught. So, a naught by ai tells me the gain in the amplitude, and if you notice this gain in the amplitude is some function which has the parameters related to the transfer function itself k and tau, and also w, which is the frequency at which I send the inlet. So, what it basically says is, if you send the sine wave at different frequencies, I am going to get different gain ratios, because the gain ratio also becomes a function of the input frequency. Similarly, if you look at the phase is also a function of the transfer function parameter tau, and again it is a function of the frequency of the input signal. So, the upshot of all of this is, when I perturb the system using a sine function of a certain frequency, I notice that the output will also be of the same frequency. However, the gain of the system will dictate what will be the output amplitude. So, if I define the output amplitude by input amplitude as the gain, right, then that gain is a function of not only the transfer function parameters, but also the frequency at which you send your input signal. Similarly, the output is going to be lead or lag from the input, and how much that is again depends on not only the parameters in a transfer function, but also the frequency at which the input is given. So, basically we will get back to this in much more detail, but I thought I will introduce this to you here because we can give you some assignments to understand this better. You could conceivably now say at each omega I will get a particular gain, right. So, because a naught by ai is this function. So, at different omegas I might get some gain like this. So, I could plot the gain as a function of omega, and similarly I can plot the phase as a function of omega. So, basically what this means is that I am understanding how the output gain is going to change, how much is going to be lag or lead from the input as a function of the system at different frequencies. So, we can generate plots like this, and this is what is called frequency response analysis. We will come back to this later. However, the key point that I want to explain here is all of this comes out of nothing more than the partial fraction expansion that you have. So, here you have this. So, the same way we write, there is C1 by, so this has two roots plus j omega and minus j omega. So, I write C1 by s plus j omega plus C2 by s minus j omega plus C3 by the root of this. So, we can write this basically as this tau s plus 1, we can write as s minus 1 over tau, right. So, then you can multiply this by tau, okay. So, that will get absorbed in your constant C3. Then you can actually do the partial fraction expansion. You can get C1, C2, C3 using the techniques that I taught you in the last class, and then basically invert this, and after you do all the algebra, which is while not trivial, it is also not very complex, it is slightly laborious, but if you do this and you get to this result here, then you have really understood how when I give sine input to a process, I get a sine output of a certain amplitude and phase. So, this is what I called as frequency response analysis. So, you could basically plot the gain as a function of omega and the phase as a function of omega, and the way this plot and this plot looks actually describes the underlying system. So, you can understand what the underlying system is by looking at these two plots carefully, and when you do that, this is called the frequency response analysis of the system. And now, since I focus on the notion of partial fractions and doing this, you do not need to know much more to analyze this lot more carefully, because you could take a second order system and then see how the gain varies as a function of omega, how the phase varies as a function of omega, and so on. And there is some standardization in terms of how do you get the gain and the phase as a function of the transfer function, which I am going to give that as a homework assignment for you to do. I am not going to explain this here, but if you do that, then you will get a much better understanding of this on your own, instead of me showing you exactly the main result. So, in fact, you would be able to guess how the result will look based on what you got for the first order transfer function in the last slide. This also brings about another very interesting idea of resonance. You might have heard that when soldiers march past and when they come to a bridge, they are instructed to break their marching pattern and then walk normally, and this is simply because the idea of resonance, where if the natural frequency of the bridge and the frequency at which the soldiers are marching match each other, then the bridge can break. So, this is not something that is just theoretical. Supposed to happen in 1831 when soldiers were marching across England's Broughton Suspension Bridge. This thing broke because of the frequency match. So, if we were to understand this phenomena based on what we have seen, so think about what does it mean to say the system's natural frequency. So, whenever you have an output y of s, so that is g of s times some u of s or I of s, and let us say your system is having let us say two poles here on the imaginary axis, right. So, let us say if these are the two poles, then this is I b, this is minus I b, and for each one of these, when you do this expansion to get g of t, you will get terms like C1 divided by S minus IB plus C2 divided by S plus IB. So, this will give you C1 e power IBT, and this will give you C2 e power minus IBT, and we have already done this before. So, this one will be C1 cos Bt plus I sin Bt plus C2 cos minus Bt plus I sin minus Bt. So, you will notice that since all of these terms are bounded cosine functions, so there will be sustained oscillation. So, this is what we call as the natural oscillation of the system. Now, imagine you have u of s, which has a pole, let us say at IC and minus IC. Then when you write this y of s as g of s times u of s, and I told you all the poles will be collected for y of s. So, you will have something like C1 by s minus IB plus C2 by S plus IB plus C3 by S minus IC plus C4 by S minus S plus IC. Now, you notice that this will give you cos and sin terms, this will give you cos and sin terms, this will give you cos and sin terms, and so on, but all of them will add together and there will be oscillation, but you will not have any term that goes to infinity, right. So, for any input where the frequency does not match the natural frequency, you will have some of these terms and it will be such that they will all oscillate, but they will never blow up to infinity. But now imagine that the C is made into B, right. So, basically what I have is I have g of s times u of s. Okay. Now, g of s has two roots, s plus IB and s minus IB, and when I write u of s, let us assume that normally if it does not exactly match the system frequency, it will be s plus IC and s minus IC, but when I make C equal to B, that means resonance, right. I have the same frequency input as the system frequency, then I am going to have s plus IC times s minus IC. Now, something that strange or crazy happens. So, now if I make this B, then the y of s now becomes s plus IB squared, right, s minus IB squared. Now you know when you expand this in partial fraction, you will have 1 by s plus IB, right, C2 by s plus IB squared, and corresponding to this you will have C3 by s minus IB, C4 by s minus IB squared. Now this term will not create any problems because this will be C1 e power IBT, but when you look at this term now and if you expand this, this will give you C2t e power minus, okay, here minus IBT, and you will get C3 e power IBT plus C4t e power IBT. Okay. Now this term and this term will not give you any problems, but look at this term as t tends to infinity now, this goes to infinity and this is bounded still, right. However, because of this going to infinity, these two terms will go to infinity. So once it goes to infinity, that means you have become unstable. So for every other frequency march past which does not coincide with the natural frequency, I will have a stable system, but when they exactly coincide, then I will get instability. And that is the reason why when they march past and that frequency matches exactly or very close to the system frequency, then you see the resonance, and you do not have to go to infinity. In a bridge like this, if it oscillates quite a bit and the material's properties are such that at certain oscillations this thing can break. So it is a very interesting and very nice way of understanding this notion of resonance from simple partial fraction expansion, and see how just when these two poles exactly become the same, you get this square term which introduces the t term in the time domain, which shows that you can have behavior that goes to instability. So if we put this all together and then we talk about a procedure to analyze an input output system. So the way you do it is, there is some input I of t to a process and y of t is what you are interested in. So what you do is you get a Laplace transform transfer function, you Laplace transform I of t to get I of s, and y of s is simply a multiplication of I of s times transfer function. Now if you want to get the initial value of y of t, you can use the initial value theorem. If you want to get the final value, you can do the final value theorem and so on. So this is how a time domain problem is converted to a frequency domain problem in process control. So with this I will end my lecture 12 and I will see you again for the next lecture. Thank you.